A characteristic of a mixture is that you can vary the amount of solute you have dissolved in a given amount of the solvent. Now this is limited, however, by something called the solubility. The solubility, or the solubility limit, is the amount of solute that will dissolve in a given amount of solvent. And the solubility is dependent not only on which solute you have, but also which solvent you have. So you see here, each substance can have a different limit. For example, sodium chloride and sugar both dissolve in water. However, the amount that will dissolve of each one of them would vary. So the solubility describes the maximum amount of solute that can dissolve in a given amount of solvent. Usually that given amount is either as 100 grams or 100 milliliters. Now before we go on to talk about the other vocabulary words, I want to talk about the words soluble, insoluble, miscible, and immiscible. So when a solid will dissolve in a liquid, we call that soluble. Now it's not the solubility. The solubility tells you the amount that can actually dissolve in the solvent that you have. Now, some solids do not dissolve. For example, sodium chloride or salt will not dissolve in acetone, the chemical in nail polish removers. Whoops, I forgot to write the word dissolve. Now, when a solid does not dissolve in a liquid, we call that insoluble. And in that case, the solid will settle to the bottom of the container. Now, we also use words that will describe similar ideas, but words that we use specifically when we have liquids. So if a liquid will mix in another liquid, for example, methanol and water will mix. We call that miscible. So the word miscible describes two liquids that will mix with each other. If a liquid does not mix, then in another liquid, for example, oil and water, then that is described as immiscible. Now I wanted to point out these vocabulary words, soluble, insoluble, miscible, and immiscible, and compare them to the word solubility. So again, the solubility is the amount of solute that dissolves in a given amount of solvent. Again, it's usually described in grams per milliliter of 100 milliliters of solution, or grams in 100 grams of solution. Now, when something qualitatively, and qualitatively means we're just describing it in words, so what we would see, there's two words that will describe a solution. We could have a saturated solution, and I think of this like a sponge. So when a sponge is saturated, it's full. And if you try to absorb more liquid in a saturated sponge, instead you would just spread it around. So a saturated solution is at its maximum solute. So it's at the limit. So you're at the top of the limit of how many grams will dissolve in a given amount of the solution. And what you would observe, if you go above that limit, then some of it will remain undissolved at the bottom of the container. Now I know in the South, where their sweet tea is quite popular, and maybe other parts of the country as well, sometimes how this tea is made, so much sugar is added that you'll actually get a layer of sugar at the bottom of the container. In that case, that solution is saturated and the extra sugar is settling to the bottom of the container. Now, if we could imagine this is actually not a static situation, the solvent continues to try to dissolve the solute, but since it's full, it's kind of like a revolving door. So the solvent might be able to dissolve a little bit of more solute in, but then some solute has to be pushed out. So visually to us, it just looks like you have a constant amount of the solid at the bottom, but the solution is actually is changing, and it's not static. It's changing very much and continues to try to dissolve. There's action at the molecular level. So if saturated again is at the limit. So here you're at the limit. And what you would observe again, if you go above that limit, we would see solids settling to the bottom of the container. Well, we also then, if you put this prefix in front of saturated, so if something's unsaturated, it means you have less than the maximum. And so this unsaturated, you're below the solubility limit. And what we would observe in an unsaturated solution is that all the solute would dissolve in your solution because you have not reached the limit. So here's a question that uses numbers and solubility numbers to help us to decide if a solution is saturated, unsaturated, or we also have this word supersaturated, which we will talk a little bit now, but in another section we'll talk about more. So in this case, this is not qualitative, this is quantitative. So in terms of a qualitative, let me change colors, it's hard to see. So if I was describing qualitative, very simply, I would say if it all dissolved, I would think that that solution is unsaturated. That's what I would expect. Now I know at the solubility limit, it will, when it's saturated, it will all dissolve at that point, but if you go above it, so if you have solid that settles, then I would think that that solution is saturated. And that's qualitatively, it's just using our observations about what's going on. But this up here, this is quantitative. So we are using numbers to help us to decide if the solution is below the limit, which is what unsaturated is, at or above the limit is saturated, and then supersaturated, which means that it's above the limit, but it's tricked. And when it's supersaturated, it's above, but however, no solid settles. Supersaturated is usually not the answer. So let's take a look at these problems. So it tells me the solubility of KCl in 100 milliliters. So there's 34 grams at 20 degrees in 100 milliliters, it tells me, of solution. And 43 grams at 50 degrees in 100 milliliters of solution. Now you might wonder why they tell us the temperature, and in the next video we'll talk about it. But temperature does affect solubility, as you can see here. At the colder temperature, you dissolve less. The limit is lower than at a warmer temperature. So oftentimes with the solubility of a substance, they give you the temperatures. So the directions also we have to read carefully. It says, if more solid is added that can dissolve, assume that the undissolved solid remains at the bottom. All right, so looking at letter A, we add 30 grams to 100 milliliters at 20. So I know the limit is 34 grams at 20 in 100 milliliters. So this is less than the limit, so this is unsaturated. Because 30 grams is less than 34. So we're below the limit, so we're unsaturated. Now the second one says we're going to add 65 grams. Again, they used to 100 milliliters, but now I'm at 50. So I find up here at 50 degrees, I can go up to 43 grams. So if I add 65 grams in 100 milliliters, then I am above the limit, which is only 43. So that means this solution is saturated, and the remaining would settle to the bottom. If I took 65 minus 43, I would approximate that about 22 grams would be settled at the bottom of the container, about. Now letter C. So letter C says I'm adding 20 grams, but look here, this time it's to 50 milliliters at 20 degrees. Well, I know from up here, I can add 34, but that's at 100. So if I could add 34 in 100, if I divided that in half, that would mean that I could add 17 grams to 50. Right? Because if I dissolve the solvent in half, then the solute also has to be in half. So at 50 milliliters, I can only dissolve 17. But in this example, I tried to dissolve 20. So that means I'm over the limit, and this solution is saturated. So pay attention, if the amount of solvent changes, then you have to also change the limit because it's going to depend on how much solvent. Now finally, we have this last question, and you can see there's lots of words. It says you add 42 grams to 100 milliliters at 50. So I could add up to 43. I see it here. So that's fine. It would all dissolve. But then look what I do. I slowly cool it to 20. Okay, well at 20, only 34 grams is possible. But does the extra settle out? No. It gives a clear solution with no precipitate, which is a solid. This is what I was talking about. This is a solution that I'm above the limit, but it's been tricked by heating it up and slowly cooling down. And so this solution, no solid settles out, and this is a supersaturated solution. Now you can see it's generally not the answer because look at all the hard work that goes into making a supersaturated solution. It's tricked. Now the question might be raised is, well, why do some things dissolve and some things don't? And one of the basic principles of solubility is that like dissolves like. Now, when we refer to this, we're actually talking about something very, very specific, and that is polarity. And so what we see is that polar substances tend to dissolve in polar substances. Non-polar substances dissolve in non-polar substances. And if they're the opposite, non-polar and polar, they do not dissolve. So another way when we say like dissolves like, we're talking about the similarities in polarity. So the closer two substances are in polarity, the more likely they will mix and form a solution or a homogeneous mixture. When they have opposite polarities, they don't mix. So for example, sugar dissolves in water. Now, one thing I memorize, and I think it is 100% worth memorizing, is that water is a polar substance. Because it's such a common solvent, it's important to remember that it's polar. So if I know sugar dissolves in water, I know they must be similar, so I can conclude that sugar is also polar because it dissolves in water. Now, sodium chloride is an ionic substance, and you'll see here's a generalization. Most ionic, and we'll talk about the most in just a minute, and polar covalent compounds are soluble in water, which is a polar solvent. Now, covalent, again, means it's made of nonmetals. And ionic would be metals and nonmetals. I'll just put M plus N because I'm running out of room there. So remember, polar substances like polar substances, including water. Now, nonpolar substances, you can see here, will dissolve in nonpolar solvents. And here is something that I remember because it's such a common solvent. Hydrocarbons are nonpolar. What is a hydrocarbon? This is any substance that contains only hydrogens and carbons. Makes sense. Hydrocarbon. Hydrogen and carbon are kind of best friends in the covalent compound world, and they like to stick together. And sometimes there's other elements, but if there's only hydrogen and carbon, it's always nonpolar. So two substances that only have carbons and hydrogens would definitely mix with each other. Now over here, polar and nonpolar. Well, we know that water is polar, right? That's something I said, memorize that. Now, but I also know that oil does not dissolve in water. So what's my conclusion? Well, oil must be nonpolar because I know that things with similar polarities should dissolve with each other, and oil does not dissolve and mix with water, so it must be nonpolar. Now, here's another thing about water that's important, especially when you're doing the homework. So it's worth reading through, and we'll have an example that goes over it. But things that are water soluble, so it's talking about water, are ionic or small polar molecules that can hydrogen bond with water. So here's what you need to consider when you're looking at molecules. Small polar molecules have lots of oxygen or nitrogen atoms that water can hydrogen bond with. In general, you need one nitrogen or oxygen for every 3 carbons. And if that ratio, that 1:3 ratio is not there, and you don't have enough oxygens for all the carbons, then even though water can hydrogen bond with it, it may not be able to dissolve it. And on one of the next examples, we'll have a specific illustration of this. So here's the first question, and you might want to pause here so that you can answer this before I go over it. So the question just says, which of these are water soluble? So what I'm thinking about soluble in water, I'm thinking most ionic substances are small polar molecules, and I know things that have 1 oxygen or nitrogen for at least every 3 carbons. Those are all things that like to dissolve. That's a 1. So letter A, lithium chloride. Well, this is a metal and a nonmetal, which makes it ionic. So yes, I would think that this one would dissolve in water. Now letter B, it's written as a Lewis structure, but as I investigate it and I look at this one here, all I see are carbons and hydrogens. So this is a hydrocarbon. And I know that hydrocarbons are nonpolar. And so water is polar, And so these two will not mix. Now letter C. I see hydrogens and carbons, but I see this oxygen here. And I know the rule up here that if I have one oxygen or nitrogen for every 3 carbons, the water should be able to hydrogen bond with it. So I have 1, 2, 3 carbons and 1 oxygen with it. So I do think that this guy should be able to hydrogen bond with the water, and therefore it will dissolve. Now letter D, again, I see this metal, sodium. Here's a polyatomic ion, phosphate. So this guy is ionic. And at this moment, I expect most ionic compounds to be soluble. Now letter F. This has carbons and hydrogens, and it also has an oxygen. But thinking about this rule, I have 1 oxygen and I have 10 carbons. Well, that is not a good enough ratio. I need 1 to 3 to be able to dissolve it. So this one will, even though it has 1 oxygen, the water will not be able to hydrogen bond enough to dissolve it. And then letter G, I see an oxygen, so I have 2 oxygens on here, and 2 carbons. Well, that's a good ratio, 1 of each. So that one water should be able to hydrogen bond with, and it will dissolve. So I expect, because they're either ionic, polar, or they have the good carbon to hydrogen ratio, that A, C, D, and G will all be soluble in water. Well, another question we might ask ourselves then, if we were given 2 different substances, would we expect them to form a solution? And remember, the definition of a solution is this is a homogeneous mixture, so that we would want them to mix uniformly. And so I remember the rule that like dissolves like, and that refers to whether they are similar in polarity or not. So what I have to do to answer this question is figure out if I think these substances are polar or nonpolar. So letter A has benzene, which is a hydrocarbon. I can see here because it has only carbons and hydrogens, and it's nonpolar. And then I have hexane, which is also another hydrocarbon. So both of them are hydrocarbons. They're both nonpolar. And so yes, I think letter A will form a solution because they're both nonpolar. Now letter B, potassium bromide. Potassium's a metal. This is ionic. And I know that ionic compounds in general would like to dissolve in water. So this will mix. Now letter C, sodium and chlorine. So this is ionic. And hexane, which I have the formula up here, is a hydrocarbon, which is nonpolar. Well, I remember that ionic substances, like polar things, they're closer to polar because of how the charges are than they are nonpolar. So something that's ionic and nonpolar are not going to mix. And letter D, there's water. Well, right away I've memorized that water is polar. And now this is carbon tetrachloride. I try to think back, and that's carbon with 4 chlorines around it. Well, I remember in polarity of small molecules, if all the outside atoms are the same element, then it's nonpolar. So I have polar water trying to bond with nonpolar carbon tetrachloride, and that is not going to mix. It's going to form 2 layers. So if you have the question, which ones will form a solution, you need to identify how close they are in polarity, because like dissolves like. Now I mentioned that ionic compounds are generally soluble in water, and there are some that aren't. For this course, you don't need to memorize the rules, but I'd like you to be aware that some things don't dissolve. But in general, you can see here There are certain ions, group 1A cations and the ammonium ion. They are always soluble in water. And then if you look at the anions, in general, the halogens are soluble, except with a few of these heavy metals. Nitrates, acetates, and sulfites, except again for some of the heavier metals. So you don't have to memorize this, but just be aware that while we generally predict ionic compounds are soluble in water, there are some of them which will form solids, or what we call precipitates, when they're in solution. At this point, for this course, I will be giving you examples when they're ionic, that they would be water soluble, not one of the exceptions to the rules.